Welcome to Cryptography and Hardware. The session is about physical unclonable functions and also random number generators. Good. First, we'll start with PUF, or physical unclonable function. Sometimes it's also called physically unclonable function. Different people have different opinion. I mean, whether it should be physically unclonable function or physical unclonable function. First of all, the acknowledgement goes to a former colleague of mine, Tim Gunesu, at the Ruhr Uni Bochum. They carried out most of the material in the slides. The challenge, why do we need PUF and why researchers actually made PUF? Many applications actually need to distinguish the devices. For example, devices need to be authenticated and also the car should be authenticated and so on. And some other authentication like, these guys you probably don't use anymore. I don't know whether you have seen these guys. Everybody is now using the mobile phone as a navigator. Now, let's say 10 years ago, there was something like TomTom or some other devices that you could use for navigation. It had the opportunity to be connected to internet as well, and also to GSM, to the traffic information. And then there was a small PC, to show you, and GPS as well. Understanding where you are and the map of different cities and different countries and so on. And then you need to actually have the map of different countries and different cities. And then sometimes you need also this request and authentication, whether this device is actually a valid one or is a hacked one, because you had to pay for every map. Of course, you notice, many devices need to be authenticated into a server or to other devices. One way of doing so is embedding the secrets in software. Some vendors include secrets as part of the binary code. Of course, some reverse engineering efforts can help and reveal this secret. For example, a lot of communities and hacking communities available that they look at the look at the softwares and they provide the hack or the serial number on some other websites that you can clone the software, or you can have the illegal copy of the software but completely fully functional. And of course, at the moment, there are some obfuscation schemes, but some of them, or most of them, do not actually provide sufficient protection, as I said, for cracking the serial numbers or scrambled data on the DVDs. Of course, I guess none of you is using VDD anymore. It's an outdated material or resource. But this was pretty much the concern of market and industry. And now the solution, which was there and still is there, embedding secrets in hardware. Let's, instead of storing the secrets in the software, then store them in the hardware. And then, of course, you need to pay more for that. For example, you need non-volatile memory, like OTP, one-time pad. Some fuses or EEPROM, some devices that you can save some secrets inside. And then the one problem is the personalization. Means that during the production of the device, some secrets should be stored in the non-volatile memory, but it should be customized. Means that if all of the devices have the same secret, then of course, then if one of them is broken or hacked, then all devices of the same company or same production are actually hacked. And at the same time, even if you do so, reverse engineering is possible. I don't know how much you heard about hardware reverse engineering. You have this chip, but you can actually open the package and have a very good and clear look at the device, at the top side of the device or chip, and then do reverse engineering and understand the structure of the chip. For example, where is the memory, where is the, for example, AES, where is the other ALU of the microprocessor, and so on. And sometimes even you are able to find the fuses and understand whether they are broken or killed or not, and even read the content of the memory by some probes, or clear the fuses, change them by some laser setups, and so on. Then this is not a clear way to store secrets in the devices. Then we look for alternative solutions. Yeah, for that, I need to shortly explain you the variabilities in CMOS properties. CMOS devices or CMOS circuits are those that most of your mobile phones, laptops, and almost every digital electronic device is manufactured with. The thing is, every device is manufactured differently. I mean, even if the devices or two chips are 100% the same and the functionalities are also 100% the same, there are super small changes inside them. You know, for example, the delay of every transistor, you know, or voltage level of every transistor. They are built completely in the same way, but there are super small differences, which is also called or referred to as process variation. You know, it means that during the process, during the fabrication, there are some variations, and this makes every chip completely individual and different to any other chip, which is produced at the same time with the same pattern, with the same schablons and everything. Yeah. Or initial state of the SRAM. When the SRAM is powered on, powered up, some random data are stored are in the SRAM if you don't clear them. Yeah? If the manufacturer did not make it in a way that it's cleared. Then this information also are different from one device to another device. You know? They are not necessarily the same way when they power up. Or the same for the flip-flop and the latches. And these varieties, if we are able to use these varieties, we should measure the electrical differences between the devices and then identify them, whether this is that device that I worked before with or this is another device. You know? And also at the same time, there should be a very low probability of two chips to behave the same. Otherwise, I'm not able to distinguish whether this was the same device that I worked with before, or this is a new device, or is a clone device, and so on. And at the same time, it should be not possible to create another device which is completely similar to that one. Yeah, it means that if I work with one device and made some information and I collected some information about that device, it should be impossible to generate another device which behaves completely the same in the same way. For that reason, the term physically or physical unclonable function is defined. Yeah, is that in a way that, I mean, the meaning of this is that you build a function, yeah, in a way that is not clonable, yeah, or it's not physically unclonable. Yeah, you should not be able to clone it fully. Yeah? And we evaluate the function in a physical structure. It means that we try to understand the physical structure of the device and evaluate it. And of course, the problem is that it's not fully deterministic, means that every time that we evaluate the physical structure of a device, we may get different results. You know? And the concept is actually something like this, that you have a path that we will see some examples, and then you send a challenge to the path and you receive a response. Yeah? And in the way that if you fabricate one chip with completely the same a structure, I mean, produced 100 times, but exact the same design is produced 100 times. For each of them, if you send this challenge, which is, for example, n bit, like 64 bits, then the response is not necessarily the same for every device. Now, this is a unique response for every device. And it's also not clonable. You know, it means that even again, if you fabricate many of those chips, still finding two devices that the response is the same for every challenge that you send to them should be impossible. You know, this is the definition of actually PUF. First, the challenge is sent inside the PUF. You know, and then there are some device-specific characterizations or characteristics. And then there is a circuit inside the device which measures these characteristics based on these challenges. And then sometimes you need also some fuzzy extractor and some error correction to generate the response. Because what you want to also have, as I said, the output is not deterministic. Every time that you send the input, the same challenge, to the same device, you may not receive always the same output. You know? Sometimes it's erroneous, sometimes it's not very reliable, and for some challenges, the output is very reliable. Some challenges, the output is not reliable at all. You know? Then some examples like optical token. I mean, I don't want to explain this in very much detail, but the idea was that, okay, the optical token, as you see here, there are some pattern, some pattern here. over the laser, orientation of the laser, and then some cameras, and getting some patterns like this out of this. Yeah? And then every piece of paper or every pattern was completely different. And then even if you produce the same thing on the paper or this optical token, they are completely different to each other. And then you should be able to recognize each of them. Yeah. But this was one of the first, let's say, concepts that you can identify. But of course, you need all these setups, the entire setup to just identify whether this piece of paper or optical token is the valid one or not. No? This, of course, is not possible if you have, for example, the CD or DVD that you have, and then you have one optical token connected to this, and then you cannot actually evaluate it at home. Yeah, that you need this setup. And some other ones, like CD puffs, it measures the variability on land or pit length on regular compact discs. You know? Because again, how it's built and how it's generated, produced is not the same for every disk or every CD. And some other puffs based on the paper. There were early works in 80s and 90s, how you can avoid counterfeiting. Yeah, of currency particularly, yeah, means that currency bills, money, or using some laser technology to scan the uniqueness of this, because you can integrate a pattern, or you can have a pattern and then you can recognize this pattern, or you can check the pattern and save in a database and so on. Yeah, but they are not the things that we can actually use in our electronic devices. Yeah. But before explaining the electronic puffs and the puffs that we can build by electronic devices, yeah, there are some fundamental properties of puffs. For example, for different puffs, the difference between an expected response to the same challenge must be large. Yeah? Means that you send one challenge to different puffs or different instances of the same puff, but the output should be far away from each other. I mean, the difference or distance between these responses should be high. If you consider that, for example, for one challenge, you have 10-bit output or 10-bit response, giving this challenge to the different devices should give you the different values, but of course you cannot say that the one response should be fully different to the other device, because the fully different means that you have 10-bit output and all 10 bits should be inverted. Then you have only 2 outputs. Yeah? But then here the idea is that to say that, okay, the metric is mean of the fractal Hamming distance between 2 outputs. Yeah? Means that you consider the output between every 2, consider every 2 outputs or output of every 2 puffs with the same challenge, and then you should say that optimal difference or interdifference should be 50%. Yeah, means that the Hamming distance between them, for example, 10-bit value is at most 10, then you should have in average 5-bit difference between every 2 output of different puffs. And for the same puff, if you have one instance of the puff, you give the same challenge again and again to the same puff, then the difference should be actually very small. This means that it should have a very high reliability. Yeah? It means that you have the single challenge, you give it to the puff many times, but then you look how many times that the outputs are different. And again, the optimal value of this is the Hamming distance between different values, 0 in average. But of course, in reality, for some challenges, this is not 0 at all. I mean, some challenges, the output is not reliable. For some challenges it is, but the idea is to have the higher or large number of challenges which have the optimal intra-distance. You know? That the distance between them is very low. That means that there is a very error and the device is very reliable. Then it should be also evaluatable, means that you just have X challenge, you give it to the puff, you get the response. You know, this is the definition. Should be unique, means that this puff should contain unique information about the identity of the physical system, means that it should not be a deterministic function. As I said, it should be physically unclonable, otherwise it's not unique. It should be reproducible, which is tied to the definition that I gave before. If you give the same x, you should get the same y, but of course, as I say, it's not always. Most of the time you should receive the y. And it should be unclonable, means that you should not be able to find two paths which provide the same output given the same input. And it should be also unpredictable, means that if you have a large set of x, y, and yi's, the large set of the challenge response pairs is also called challenge and response pairs. If you have a large set of this, then you should not be able to identify or find out or predict what is the output of the path before, without giving really the challenge to the path. And it should be one way, means that if you have y, you should not be able to calculate x. It should be a one-way function. Tamper evident is something that we do not deal with a lot here. Means that if you change something in the condition of the device, its behavior should not change. For example, change the temperature, change the voltage, or run it in a very noisy environment, then it should be also tamper evident. No? The application of the path requires two phases. Enrollment phase means that in a classic scenario, you have, when you generate the path in the company, you make a list of challenge of response pairs. Of course, not a full list, because, for example, the challenge can be 64 bits. Yeah, you cannot get all the responses of 2 to the 64 cases, but a large set, large set for authentication. You get for every chip this database, or you make this database for every chip. And then what you do when the chip is working in the field and it needs to be authenticated, then the server selects one of these challenges from the list, send it over the air to the device, and device sends the response back. And then the server checks whether the response fits to here or not. Of course, it might be one of the non or unreliable challenges, and it should be repeated a couple of times. And the challenge which is used should be, of course, deleted from the list. Then you can see that, okay, the number of times that the authentication can be done is restricted and limited to the number of challenge response pairs that we have in the list. And then one application is system authentication, as I explained. Then it avoids the counterfeiting. Means that you have built, for example, this TomTom device, and then you make a clone of it using your own, for example, microcontroller, or even the same microcontroller, and then even you make a full copy of everything, but then this device cannot be authenticated in the server. Because then there is the same path, you cannot copy the same path. And then another application is to generate the secret keys. Means that it's not like this. It's not the challenge response pairs, but a set of and a fixed set of challenges are actually used inside the device to generate to look at the response, and then this response goes to a fuzzy extractor and also error correction to generate the secret key. Then in this way, you do not need any non-volatile memory. You generate the key by the device, and then every key of the device is actually unique to itself. But this will be, for example, the secret key, and then the public key is generated inside the device and is sent outside, and then the authentication can be performed. And this is what I already explained, the intra-difference and interdifference. This was actually the interdistance that was between giving the same challenge to different chips. And then what we said, the 50% is the ideal one. That of course it never happens. It will be like this, means that some challenges has a higher distance and some others not. This is the frequency. And the best would be actually if you have here 50%, and there's the intra distance, means that as I said, how many times you have the same output which is provided by the same device if the same challenge is repeatedly given to the device. And then Of course, as I said, this will not be also ideal, and then something like this. And then we would love to have the intra distance close to here, close to the y-axis, means that the distance of 0 has the highest frequency. But then if you look at the point that these two curves cross each other, then this is the optimal identification threshold. This is what I already explained. Yeah, to support key crypto primitives, you have the puff and the key extracted over the error correction and fuzzy extractor, and then it's used for crypto. And as I explained, you don't need to have any non-volatile memory to store the key, and the problem of the reverse engineering and so on, because the key is not there. It will be just generated every time that you need it. I don't want to get into the application of the PUF, because how the PUF is used for the key generation is something that we do not deal with this in the lecture. These things that we see here, the secret key replaced by a PUF construction. Yeah, I mean, something is written here, SCA resistance is something about sidechain analysis resistance. Is something that we deal with in the next session. Yeah, it's about the physical attacks. Yeah, I mean, in this session, we do not deal with the attacks or sidechain attacks on any kind of devices, including PUFs. One way of integrating and building PUFs, one of the ideas is back to the concept called arbiter PUF, yeah, which is, I think, the most famous PUF which is built. It works like this. Yeah? Here you have some stages, and these stages are actually some switch boxes or switch blocks. Means that one line that you can see here, one signal, is given to this box, and by this control signal, if the control signal is 0, then this line actually goes like here. Yeah? But if the control signal is 1, then they are crossed. Means that either they go directly or they swap, although they are the same signal because they are connected to each other. Yeah? And then you repeat this many times, and they are actually the challenge bits. Yeah? Means that this is the challenge. Every time that you select a challenge, you build a different path. Some of them they pass, some of them they cross. Yeah? And each of these switch blocks has a different delay. Yeah? Either, for example, if they pass, like this, the difference, there is a particular delay difference between these two lines, between the line upper and down part. And if they are crossed, another delay will be added to the difference between them. Yeah? And then what happens, they are connected to one component, which is called arbiter. And the arbiter is nothing than just a latch. Yeah? Yeah, the arbiter is similar to one latch that you learned before. Yeah, how we build a latch, like the NOR gate or NAND gate. One latch with NAND. And if at the start they are both 0, then the outputs are both 1, which is the invalid value for the latch. Yeah? But if set becomes, or S becomes 0 to 1, then what happens? Then you know that here 1 actually comes here, and both of them are 1, the output becomes 0, and this 0 actually keeps this 1. Means that then afterwards, R changes to 1, it doesn't change the output. Because 1, 1, and this is R or S prime, R prime latch, 1, 1 doesn't change the content of the latch. The arbiter checks whether S comes first or R comes first. If S comes first, then this will be 0, 1, S, and if R comes first, it will be 1, 0. If they come exactly at the same time, it depends on the the internal structure of the gates. Yeah, and this is the structure of the arbiter. And then what happens if there is a positive edge, from 0 to 1, the trick signal is given to here, After some time, based on the challenge, either this one sees the positive edge first or this one sees this first. And then the value of the arbiter says which one was the faster. And if you change the challenge, this will be, of course, different. But the point is, the delay between these depends on the process variation again. From one chip to another chip, the delay between these switch boxes, whether this one is faster or this one, or the other one when they pass, they depend on the implementation. And then this will be a kind of a puff, that if you give the same challenge to different puffs, exactly different implementations of the same puff, then the arbiter or the output, the response is not exactly the same. But this, what you see here, is only one bit response. 1 bit response, of course, is not enough for authentication. Then you need to have many instances of this inside the chip, and you can give them the same challenge. And then for the authentication, and then generate a lot of responses and use it exactly as a puff. Now, to learn this better, I provided an implementation for you on the FPGA. You may say, how can we implement it in FPGA? I have here a puff instance, and a lot of hard coding and macros are used. One important thing to consider is that, this is the same signal. And if you build such a thing by the switch boxes and so on, the synthesizer will say, this is the same signal, I remove them. You have to ask the synthesizer to not remove this, by some properties and some constraints like keep and keep hierarchy and some other things that we will see now. Good. What I have here in the arbiter puff, n is the number of stages. Clock, why we need a clock, I will explain. And there is a trigger signal. This signal which changes from 0 to 1 at the start. And this is the challenge, which has n bits. Response bit, which is the output, and response ready is 1 bit to indicate, okay, the arbiter built the output and you can take it. Why we need this? Because you don't know how many clock cycles and how long you should wait. Then you need 1 bit to say the response is ready. But what is this? How can you say the response is ready if both of these lines are 1? Means that both are arrived there and the arbiter made the output, then you can take the output. Then I instantiate switch chain, with again n stages. And the switch chain has the input top and input bottom, the lines here, input top, input bottom for every of them. But here at the start, this is a full chain, input top, input bottom, and here output top and output bottom. And the challenge, and of course it goes to the NAND latch, which is the arbiter, which I have explained. If you see here, what I have a register for the trigger, because the trigger should be absolutely without any glitch. Glitch is clear to you, no? Glitch, it should not change. Should be a register. You can of course put the register before, but then the clock and the trigger signal, and then the trigger which is in the register is given to the switch chain with the challenge, and the output path through path top and bottom are given to the latch, and the latch has Q and Q bar, 2 outputs. I don't need the Q bar, I just call it open. And this is the response ready, which is the AND between both path top and path bottom. As I explained, if both of them are 1, then means that their response is ready. Okay, we first look at the arbiter. The arbiter is nothing else than 2 NANDs. If you remember, I had the LUT2. Do you remember the LUT2? And then this is the value, the lookup table. This is a NAND because I think this is the first bit, second bit, third bit, and fourth bit. And all the outputs are 1 except when both of the inputs are 1. This is a NAND. And then they are just cross-coupled. There's the input S and the QF. QF is given to is coming to the output of the other one. this is exactly what you see here. Yeah? For example, this is S, this is R, this is one of them is Q false and Q true or other way around. And then you need to just instantiate it like this, connect them like this, and of course the synthesizer will complain, yeah, because you build a combinational loop. Yeah, then you need to take care of this. I will explain later how to avoid the complaint. Otherwise, it will not generate the bit stream for you. Now, the only thing to see now is the switch chain. The switch chain is made by a couple of switches. Means that the switches, what you see here, are just instantiated n times, each of these switch. And the switches are having, input top, input bottom, output top, output button, and the challenge bit. Now, how this switch is generated, again using some macros by LUT. Yeah, there are many different ways to do so. And everything that I explained here, it might be not necessarily working for every device. You remember probably LUT. And then you can have a look at LUT 6.2, and this is the internal architecture. And I think I already explained this before. Every LUT is just some registers, with some multiplexers. And the registers store the content of the lookup table, and some multiplexer tree define where you have the output. The idea of this is to use one LUT 6.2 as one switch because it has two outputs, and then select just two inputs. In this case, what you see here, the inputs are selected to I0 and I1. I0 and I1, which are connected to both LUTs. And then one challenge is actually connected to I5. To I4, which is also the last bit of here. Yeah, and then the content of the lookup table is built in a way that it doesn't matter always what appears at I top appears on output top, and what appears on I bottom appears also on the output bottom. Means that this is exactly path through. I mean, it doesn't perform any operation, but then this construction actually should stay as it is. Should not change the order of the bits. Should not make it smaller, or should not actually optimize this. These are necessary for the synthesizer. And what you need to do, you need to actually say keep hierarchy is true. In this module, it means that it should keep the hierarchy. Keeping the hierarchy, what does it mean? It's not dedicated to FPGAs, any hardware design. For example, you have a module which has some other modules integrated or instantiated inside the module. This is, for example, module 1, this is module 2, this is module 3, this is module 4, and there is another one, module 5. What you can say, I mean, you can generally or globally say hierarchy should be kept or keep hierarchy. It means that the elements which are in module 2 should never come out and be optimized with some other components and the gates which are here and with the other components of the other modules. Means that if you make an AND gate here and keep the hierarchy, the AND gate should stay as it is, should not change. Of course, inside the module 2, if you have many different gates, of course, it can be optimized. Unless you inside module 2, you say, if I instantiated AND gates or some other gates and components, they should not be also merged with any other thing. Now, what it makes sense here, keeping the hierarchy. There is in VHDL, and for Xilinx, you should do it like this. It's only valid for VHDL and only for Xilinx. Means that if you want to do it for ASIC, this is not the way to do that. For every synthesizer, you have to follow a different procedure. You need to define the keep hierarchy as a string, and then say that they keep hierarchy of a structural. What is a structural? This is the name of the architecture here. The name of the architecture is true. And you may ask me, how did I get it? You need to find Xilinx constraint guide. Yeah. For example, here, keep hierarchy. And this is actually an old one. And it's also explained what happens if you say keep hierarchy here, yes, you don't say keep hierarchy yes for the others. And then it also says if you have VHDL, you need to say first define the attribute keep hierarchy as a string, and then say it like this, that attribute keep hierarchy of the name of the architecture as an architecture is either true, false, or soft. For each of them there is a difference. In Verilog, there is a different thing. Then we say keep hierarchy yes means that what is inside loot 2 will not be merged with anything else. It stays exactly as it is. You can see here, I did not apply them, but there is another one, keep. Not keep hierarchy. For example, keep. For some signals, it should not, for example, you want to keep one signal and then it applies only to signals. Then again, you can define the attribute keep as a string and then say the attribute keep of signal name, which is a signal, is true. One more thing is to do not change the order of the inputs of the loot. I think it's lock pins. Lock pins constraint is applied only to a specific instances of loot symbols. Then you need to, for example, here again define the attribute lock pins, and then say the name of the component or the label name and say that it's, for example, lock pin also. What does it mean? Although you define it like this, the synthesizer may change the order of the bits. And of course, changing the order of the bits means changing also the content of the lookup table. But that's okay. The synthesizer understands this and then changes it in a correct way. But why the synthesizer changes it? Actually, this is useful for the routing and placement. For example, the placer put this loot somewhere and say, okay, if the order of the bits is not like this, if it's in the other way, I can route it easier and better and faster. But sometimes you don't want this to be done. Then you need to also ask the synthesizer to not do it. Good. That's all. And I already built this for you. You have already this, and you can change it by yourself. And I also adjusted the framework in a way that you send 8 bytes, 64 bits, because I instanced the arbiter path for 64. And then it sends you 1 byte. Of course, just the LSB is the response. But what are the important things? Some constraints. You remember we had some constraints and constraint file saying that which pin is connected to which signal, which was up to here. Now you see I have a lot of other properties. Look here, I have those many properties, which actually we should help the placer and router to place these loots in a correct position. Otherwise, if they are far away from each other, the delay difference between them, the delay between, for example, this upper pad and lower pad, or between them, they will be too large that the difference between them will not be different for every device. It means that they are always, for example, the upper one is larger than the below part, independent of the process variation. And this makes what? This makes in a way that if you send the same challenge to different devices, you always receive the same response, completely independent of the process variation. It means that the inter distance actually will be very low. Yeah? Then what we do here in Vivado, you have also this, this opportunity. Yeah? Then you say set property, location. You can say that, okay, where I want this LUT to be placed, and you get the cell. You may say, how did I get this? I mean, you get the cell, and then you need to find it out. How? If you look, there is a puff instance, and then switch chain, this is the module, and inside the switch chain, gen, yeah, 0, and then dot SW, and inside the SW, I called this LUT also SW. Yeah. And this selects the first switch in the chain. Yeah. And I said the location of this should be in this here. I will show you the position of the slices and so on. And there is also a bell. What is a bell? Remember, there was inside the slice, there were 4 different LUTs. You can also select where this should be placed, either LUT A, LUT B, LUT C, or D. Yeah? Here, this is B, and I selected only B to be done. And also don't touch means that, okay, don't touch true for this cell. Yeah, don't touch true means that it does not change the order of the bits, does not optimize it, and so on. Then this, of course, you need to write it down by some programs. You see here x30 and y2, and then x30 and y3 means that in the same line, I will show you now, they are implemented. Yeah? Then up to y36, here y65. Some of them are just comment, I mean you should ignore them. And also you can place the arbiter, no? The x and y, which are the arbiter. You see here I instantiated x and y, these 2 LUTs, and also they should be also don't touch to not be optimized. No, I can open the implemented design. In the meantime, I can show you also something else. This will be implemented and will be synthesized and implemented, not a problem, but you cannot generate the bit stream. Again, still the DRC check complains that you have a combinational loop and so on. How to avoid this and how to force the synthesizer or Vivado to build the bit stream, there is something that you can see here, utilities. And TCL means that there are some scripts that before the generation of the bit stream, you can actually add. This is a file which is added to here, to utilities and pre-TCL, and it sets property, severity, warning, yeah, and get DRC checks of LUT. It means that any error which happens ignores this and makes it as warning. Otherwise, it doesn't generate the bit stream. And this is the entire architecture of our FPGA. Yeah? What you see here, each of them is one slice. I mean, I can even increase here. You see, each of them is one slice. Of course, this is a conceptual view. And these are the LUTs. You see here, they are the LUTs inside every slice. And if you more carefully see, the number of the slice x30y3 is given here. And if you go down, the other one is a slice x30y2 and so on. And they are implemented after each other. This orange, this sometimes it's hard to work with this tool, yeah, sometimes. This blue, orange ones that you see here, it means that actually they are implemented and they are used. It exactly tells you this switch. Yeah, you see the name is WLUT62, and it tells you that, for example, how the lines are connected. For example, nets, you see C and how they are connected. And the name is Gen 0SW. This is the first stage, the first switch in the chain. And then you can follow everything actually, how, for example, where this guy is. You know, I mean, when I select this, it should be actually this guy. I think I'm not in the correct one. Probably is in the next one. Yeah, it is here. And even the formula, because it's a net list, you can also see the bell is B6 because it's the B. Here is A, B, C, D. And you can also see the content of the lookup table. I think it's properties. You see this, the init value. This is exactly what we have defined. And then because the order of the bits is not changed, then it's skipped like this. And based on this, you can build the path, you know, or any other thing that you want to, for example, put anything inside a particular slice or not. Now I can put this on the FPGA. You may have a look. I need to send something, and you see most of the time is 0, sometimes 1. Yeah. Can have something like this. I mean, of course, I do not change or check, because first of all, you cannot check whether the outputs are connected or not. Yeah, because it's the function that is actually unknown. But you see, for example, I selected something that it's sent a couple of times or many times, but the output is always, for example, 0. Then you change something else, and the order of the bits which are sent will be different. You see sometimes it's 1, sometimes it's 0. Yeah. And if you want, I mean, you can have the bit stream and configure it in 2 different devices by yourself, yeah, because each of you has the same board, and then check for which output, for which challenge you have different outputs and so on. Yeah, this is the way, or this is the one way to build the puffs on the FPGA. Then one problem of this puff or arbiter puff, which is super known or highly known, is that you can easily build a machine and learn this behavior. Now, there are some models for the machine learning, yeah, and then you can collect a set of challenge and response pairs and build a model which actually predicts the output with just 4% error. Yeah? And then the idea was that, okay, it's like this, then let's make it more complicated, then have a couple of them and then XOR the output. And of course, the challenges should be the same. Yeah? I mean, you give the same challenge to, for example, 4 instances of this, and then the output are XORed, then you generate one single output, and it's called XOR arbiter puff, but there are still machine learning attacks on this. Very easily, you can still build the model and predict the output with a high probability. And then many people try to make this more complicated by connecting this response and use it as a challenge to another set of the arbiter puff and so on, and makes it more complicated. The problem is that if you make it very much complicated, of course, the machine learning attacks are not possible to be performed, but at the same time, you decrease a lot the reliability. Means that the system will not be reliable anymore because, for example, this output, which is not fully reliable, is used as a challenge, for example, in other stages. And then when the challenge is not reliable, then the output of the next stage is also not reliable, you know, because the input is not reliable. Then there is a trade-off here. Either being learned easily, and at the same time be reliable, or be resistant against most of the machine learning attacks, but at the same time useless because it's not reliable. I would say somehow the research in that area is somehow stopped. No, people believe that it's not really possible to build arbiter puffs or different variants of the arbiter puff at the same time that they are resistant against machine learning and reliable. And then another scheme is ring oscillator puff. Yeah, ring oscillator, you for example, you have one AND gate and it oscillates all the time. Of course, the frequency of oscillation depends on the delay of the inverter or the chain of the inverters, and some edge detectors and the counters and so on. But it's not the best way because the frequency roughly can give you the response, but it's highly affected by the environmental noise. And then the idea is that, okay, do it something different, somehow differently, means that have something and then divide the frequencies, because when the temperature goes up, or the power or the voltage goes up, then this oscillates faster or slower. And if you divide the frequencies roughly, you get the proportional one. That should be okay. Or just check whether which one is faster, which one is slower. No? Another one, or let's say like this, which is the most known ring oscillator puff, is that you have a couple of ring oscillators, of course, with some enable signal. You see here, you can enable or disable them, and then each of them produce one clock signal with a certain oscillation frequency. And then what you have here, you have a large multiplexer, and by single input, for example, 8-bit, you select one of the 256 oscillators at the top and another one from the 256 oscillators at the bottom side, and then they are given to the counter. Then for a certain period of time, for example, 10 clock cycles of the general clock of the system, then you count here based on the clock which is given through the multiplexers, and then you stop after, for example, 10 clock cycles, and you check which one is larger than the other. Then the output is 0 if for example, this one is larger or the other one. Then this is one way of building the puff, and this is actually your assignment. You need to build this. We will deal with that later. But it's easy to implement, for example, ring oscillators and the FPGAs using the lookup tables and inversions and so on. But of course, it can be also learned, because it's not a super complicated machine, and there are not many parameters. And if you select in machine learning attacks or machine learning generally, if you have enough number of layers and enough number of challenge and response pairs, then usually you can learn the behavior of the device with a high accuracy, high prediction accuracy. Another thing is dual port RAM that you have already learned. You know how the dual port RAM works. I don't need to explain to you, how this works and the available modules in Xilinx. The thing is, here there is a cell every bit of inside memory. Of course, how does it work? It's a SRAM base, or cells are like the flip-flop, means that cross-coupled inverters. And then as you learn, there are two different ports that can work completely individually. At the same time, you can read and write. But what happens if you try to write one with one of the ports and try to write 0 with another port in the same cell? Which one is stronger? And this, for some bits or some addresses, then this depends on the device. For some addresses, it's completely deterministic, because of as similar to arbiter puff. The delay between two lines are very far away from each other, then the process variation does not affect them. But for some other locations, these delays are very similar to each other, and then the process variation decides whether this saves this, the port 0 is a stronger or port 1 is a stronger. Then every cell and every bit of the memory can be checked, and this is called BRAM write collision. It means that you write at the same time there with 0 and 1 here, yeah, or fully 0, 0, and here FF complete, or depending on the size of the port. And then you read from there afterwards whether it was 0 or 1. Yeah? And then this will be the challenges. Of course, not all addresses are actually possible, because the address becomes your challenge. Not all challenges are possible or available. Good. Another one, which is also well known, is called SRAM POF. Means that after the power up, as I explained, you don't know what values are actually stored in the RAM. Then if you read them, and for example, the challenge will be the address at which position you read. For some memory cells are fully deterministic, means that it doesn't matter how many times you turn them on and off. The output is always, for example, 1. For some of them, again, depends on the temperature and the environmental effects will have an effect on them, and then they are not reliable outputs. And then for every device, you need to identify which addresses leads you to deterministic or let's say reliable outputs. Yeah, and this is called SRAM POF, and then most of the POFs which are available now in industry, I mean, if you look at most of the POFs that they are advertised are based on SRAM POF and other variants. And apart from this SRAM POF and the other POFs that we discussed here, some other POFs are completely challenge independent. Means that during the process variation, the devices are built like that okay, some bits are either 0 or 1, but it's completely depending on the process variation. For example, suppose that you have a 28 nanometer technology, and then 2 lines or 2 pins should not be closer to each other like a particular threshold. Let's say not smaller than 100 nanometers, 2 lines. And then if you violate this, then there is no guarantee that these 2 lines become completely separate from each other in the metal layer. They might be connected to each other. And then if you build a pattern that you actually intentionally violate the requirements, but then it's not predictable which lines will be connected to the other one, and then depends on the process variation. And based on that, then some kind of POPs are generated inside the chip, which is completely challenge independent, but it's completely fixed. And most of the time, they are also somehow reliable. It means that it doesn't matter how many times you read this value from these 2 lines. I mean, always they are either connected or not connected through the process variation. There are some also results. I mean, we don't want to discuss about them from the SRAM POFs. The SRAM POFs that they are embedded inside the microcontroller, or there are tiny separate modules individual that you can buy and have it in your PCB as a SRAM module, where the results are roughly comparable, and you can compare them. It's not far away from each other. And another POF construction is also called butterfly POF. It helps. I mean, you can implement this easily on FPGAs. The one problem of the SRAM POF is that you cannot use them in the FPGA easily, because in the FPGAs, the block RAMs are actually have a initial values. If you remember, when you build or instantiate the block RAM, you give the init values. For example, what we use for the SPARCs of the AES, or for the T-table implementation. Then the initial value of the BRAM should be given. If you don't give it, then the synthesizer would fill it with 0. It means that after the power up, the value of the block RAMs are already deterministic. It means that you cannot use the value of the block RAMs as the SRAM. And then either you can also build the cross-coupled inverters by yourself inside every LUT. This is also possible. But it's very strongly depends on the placement and routing, not on the process variation. And then one other option is to build the same way by cross-coupled latches. Means that you have 2 latches, not 2 inverters. And then you need to think about this. The clear or both are 0, and then there is a preset and a clear. And there are latch, not the flip-flop. The output of the Q is the input of D, and G is the enable signal of the latch. And at one point, you first preset one and clear the other one, but then you leave it till it oscillates sometimes, till it gets stable, and then the value which is stable inside this butterfly puff will tell you that, okay, the deterministic value is 0 or 1. Yeah. Similar to SRAM puffs means that you actually don't have, you do not give any challenge to this unless you have some addresses and select some of the outputs and use this as a challenge. Yeah. There are some promising results. I'm not much into this to check what is the current status of this research, but the first result was very promising. I'm not sure whether this is valid on every device and it can be reproduced. Yeah, but the good thing is they can generate on the FPGAs. And what they have done, the original authors used 36 FPGAs, which is relatively low number of devices to check statistically the behavior of the puff. Some summary: the physical unclonable functions are unique features for some device identification. Sometimes they are not used very often in industry, and there are some difficulties to use them, particularly for authentication, but for key generation is absolutely a good way to do. There are many different ways to do that, as I explained, but mainly based on the delay of the circuit or delay inside the circuit, which might be affected by the process variation. And one point is that the puffs need to be physically unclonable and also mathematically. It means that if you build a model, it should not be possible to actually clone them. And most of the time, these puffs are susceptible to environmental influences like the temperature, supply voltage, some working in radiation, and the radiation, and so on. If you want to use the puff as an authentication mechanism, then extensive puff profiling requires, or is required, means that you need to build a large set of large set of challenge and response pairs to be able to use them in practice. Then the next one, which is highly also related to puffs, is about the random number generators. Means that how can we generate random numbers in hardware? We know that many systems actually depend on random values, like some protocols, like the secret key generations. For example, you have seen that we need to have a puff to generate the key, but how about generating some random numbers, for example, for protocols like Diffie-Hellman key exchange protocol? Then you need to generate some randoms. And then there are some definitions of the random numbers, or RNGs, random number generators, that it should be, of course, independent of each other. You need to have the independence, and should be uniformly distributed, and it should be also unpredictable. It means that if you have a large set or sequence of the random numbers, that should not be able to predict the next one with a high probability. There are many types of random number generators. You see here, true random number generators or pseudo-random number generators. Some of them are purely based on the pseudo-random. Some of them is a hybrid between true and post-pseudo-random. Some of these true random number generators are not really physical. Some of them are physical. Some of them are hybrid and pure. We deal with just pure physically true random number generators here. How we can build them. There are different specification of them, deterministic and pseudo-random. For example, you heard about the PRNG. I'm pretty sure. You can LFSR, for example, or an NLFSR. We talked about also trivium before in the lecture. Then you can use also trivium or stream ciphers for as pseudo-random number generators. But the true random number generators, the problem of them that we will see, they are highly slow. Means that every time that they want to generate a random number, it takes some time with random bits. Means that they don't have a high throughput. But then usually in applications, they are used like this, that there is a PRNG, which is super fast, yeah? But then there is a TRNG which generates the seed for the PRNG. Is that if you seed the PRNG with a good frequency, and this frequency is actually low enough to generate the number of true random numbers by a TRNG, which is super slow. You know, then usually you need to have a TRNG which generates the seed for you, which is a slow, and then use this seed for the PRNG to generate the random numbers in a fast way. There are a lot of discussions about the quality of random numbers, about the entropy of them. There are a lot of statistical tests. Now, I don't go through all the details that we have in the slides. If you are interested, you can have a look by yourself. But for example, here, tossing a coin, how much entropy per trial you can get if you have, for example, 10 coins. And for example, can you get 100 random bits per second if you have, for example, just 10 coins? And if some of them are, all of them are not fair, some of them are biased, some of them are correlated, and just a few of them are fair, some of them are manipulated. And there are a lot of discussions and the formalities about the generation of the random numbers. And then at the end, if some of them are actually manipulated, some of them are correlated, some of them are actually biased, what happens if we easily just XOR some of them in order to get a 1-bit output? This is something which actually happens now in practice, that if you do not have a unbiased output, then you generate a couple of them which are completely independent of each other, and then you XOR. Then, there is a way, of course, but tossing a coin, of course, is in practical embedded systems. You cannot really do that. The throughput is also pretty low. But we have some schemes in electrical or electronic domain to really generate random values. Most of the times, there is an entropy source inside a device. For example, I can shortly explain you. For example, you have a level of the voltage, VDD, and then it has a noise, a small noise, because it's never, for example, at 1.1 volt, you can never see that it's 1.1000000 volt, no? There will be a few, for example, 1 millivolt, or even a smaller than millivolt fluctuation, changes. And if this fluctuation is not really periodic, and it's affected by the environment, then you can have some devices to measure this fluctuation. And then turn it to digital, whether it's higher or lower than a value, and then easily generate a random bit or some random bits. This is a simple thing as an entropy source. But then in a formal way, there's something like this, that the source of the digital noise or analog noise, which is changed to digital, then you need some pre-processing algorithms, and then also what you need always in true random number generators, an online test. There should be some device. You don't need to change or check the output of the PRNG, because the PRNG is a deterministic function if the input is null. But if you have a TRNG, you usually need to have another module inside your circuit to check in an online way what is the entropy. Everything is fine, or is always 0 is generated, or always 0, 1, 0, 1, 0, 1 is generated. Because if every time you have 0, 1, 0, 1, 0, 1, of course it's uniform, but it's predictable. For example, here, the thermal noise you can measure and turn it to digital. You can use the chaos in analog circuits. Of course, this is out of the scopes of the lecture. You can have jitter in the oscillator on the clock, because the clock generators are not fully, let's say, stable. There are some changes in the phase. There are some changes in the period. And of course, when you say I have a clock generators of 100 megahertz, of course, in average is 100 megahertz, unless some crystal oscillators are used, because crystal oscillators are known to be super accurate. For example, they are used for the clock, for example, for watches that you have, wristwatch that you use. There are crystal oscillators. They should be actually super stable, and super fixed with respect to the period. But phase may change, and also cycle to cycle jitter. I mean, there are definitions here, and you may have a look by yourself later. But if you are able to measure this, then it's actually a random behavior, and it's again an analog from, of course, this is a digital signal, but it comes from an analog domain. And then again, keep in your mind that never in practice you have this sharp peak, yeah, of the changing of the voltage for the clock, yeah, instead of this, there will be always something like this, if you are actually lucky. Otherwise, it will be something like this. Yeah, some bumps may happen here. Yeah, and sometimes because of the bandwidth will be something like this. This actually changes, but it slowly changes to here. Again, it changes down and then it slowly comes back and so on. Yeah, sometimes this is also not sharp. This will be like this. Then if it's like this, it becomes also something like this. Yeah. For every device and every package implementation, everything will be different, and this shape will be different, and at how much bump it makes, it affects on if you wanna measure, for example, the jitter. Again, some metastability that you have two stable values, 0 or 1, and it hardly goes up. When it goes up, either it goes to a stable 1 or a stable 0. Then exactly at the time that you measure, for example, if you want to change from a stable 0 to a stable 1, I mean, it takes some time, it goes up, and it takes some time to go down, exactly like this clock, which I have drawn. Yeah, and then the point is, for example, just measure the time that it changes from the 0, a stable 0 to a stable 1 or other way around. Yeah, many different things to measure. But one of them that is very famous is ring oscillator. It's similar to ring oscillator puff. Yeah, the same concept. Here you have here the ring oscillator made by some inverter chains and some reset signal. I mean, similar to what you have seen. This is the AND gate and then the reset signal. And here you have a flip-flop. Yeah, at one point in time, you say, hey, I want to sample. And then you sample here, and then you have one output. And of course, one way is to just make some of them and XOR the output, because you may not always get an uniform number of 0 and 1s. And one more thing is that probably it's here. These oscillators should have a different frequency. Yeah, I mean, they should be, of course, they should be very similar to each other, but not highly similar. Yeah. Otherwise, you always make the same output here. One more thing is that the frequency with which you sample, because you sample based on what? Based on the clock of your system. Yeah? This should be independent of the frequency of their oscillation. Otherwise, you always get the same pattern. And then the bad thing is in devices, yeah, which are very noise-free. This is a bad thing. Yeah? When the device is noise-free, then the frequency of each of them will affect the frequency of the other one. Means that after some time, you see that they are somehow synchronized. No? They don't have exact the same frequency, but there will be a connection and relation between them. And of course, if you have a clock of the entire system and it's routed everywhere, the clock of the system will also have an effect on here. Means that if you have here the clock working one, this one also affects on this one and the other one. The problem actually happens in the puff. Yeah, in the puff, if we discuss, you have a couple of different oscillators, and if you turn off some oscillators, which are just close to the oscillator that you want to measure and you want to sample, then it has an effect on the frequency of the other ones. Yeah. I don't go to all the details of here about the quality assurance, but one thing that to consider, there are a lot of tests that you can do, and there are a lot of discussions, very lot of discussions, what you can do. There is a FIPS, no? But it's a bit old, but there is a revision 2001. There are a lot of tests that you can do. It means that if you build a PRNG or TRNG, then there are a lot of tests that you can check during the construction, yeah, during the design, not during the manufacturing. I mean, not during the operation, not the online tests. They are the offline tests. And the most important and the most famous one is the NIST. There are a lot of tests, for example, 16 tests that you can do to check the random numbers. And it's actually not only dedicated to TRNGs. You should also do it for the PRNG. If you build a PRNG, then you should actually also test the PRNG by this NIST test and to make sure that everything is actually fine. And recommended length of sequence is 1 gigabit. That means that you should generate a lot of data to be able to run these tests in a good way. As a summary, TRNGs are important for security products, but require additional hardware. Several effects of digital circuits can be used to generate random numbers. I mean, either analog domain or digital domain. And we should be very careful with respect to the tamper resistance, because we easily can manipulate a TRNG in a way that the output is completely deterministic and it's always 1 or always 0. And then if it's the way, then you know that, for example, the seed of your PRNG is always 0 or always 1. And if you turn off and turn on your device, always the same sequence of randoms are generated. Of course, they are random, but if every time that you turn it off and on, then the same sequence is generated. These are dangerous things. And for that reason, as I said, usually the output of the TRNG should be checked online. And of course, if you build something as a random source, then of course you need to run a couple of tests and a statistical test to check whether the quality of the random numbers are good enough for different applications.